Alright, let's use finite differences to determine the type of polynomial function that can model each relationship. Okay, so Michelle earns $200 per week plus 5% of sales, right? And her sales are associated with her earnings, right? So sales are an independent variable, earnings are a dependent variable, and we can understand that earnings, I'm going to use E, let E of S represent earnings after S sales in dollars. Okay, and we want to figure out a relationship here. Okay, so they are asking us to model this as a polynomial function. We know that polynomial functions will have a constant finite difference. So for us to kind of figure out what the polynomial function is, let's figure out the constant finite differences. Okay, so we know that finite differences can be expressed as delta y over delta x, right? You notice that each difference here is by 500. Okay, so the delta x value will be constant, so delta x will always be 500, right? Let's figure out our finite differences, right? So I'm going to call this my first differences, and this is my first difference is 1, this is my first difference is 2, first difference is 3, right? First difference is 4. I think it'd be easier if I construct a table just to kind of show you guys this out, right? So let's just reconstruct this table just so we can make a clearer picture here, right? So this is sales, this is earnings as a function of sales, right? We have 0, we have 500, we have 1,000, we have 1,500, we have 2,000, right? And here is 200, 225, 250, 275, and 300. Okay, so let's take a look at our first differences, or our first finite differences. I'm going to subtract these two, so we get 225 minus 200 over 500. Okay, so in this case we'll basically get 25 over 500, which basically will be, if you punch this out in your calculator, right, 25 divided by 500 is going to be, 25 divided by 500 is 0.05, right? So you're going to see that is going to be constant throughout, right? 0.05 and so forth, right? So 275 minus 250, let's get rid of this notion here, over 500 is equal to 25 over 500, so 0.05. So you can see that the first differences are constant, right? So the first differences are constant, and if the first differences are constant, well, we also know that the slope delta y over delta x is basically the slope of the function, or the rate of change of the function, right? But we can also refer this to how we discussed the finite differences in leading coefficient initially. We know that this is going to be a linear function because the first finite difference are constant. So we're going to express this as E of s is equal to ms plus b instead of mx plus b. We're just using s as our independent variable. And you can understand that this guy here is our leading term. Okay, because it's going to have power 1. This is going to be s to the power of 0, but we don't write it because it's 1, right? Now this is going to be our leading term, and we understand this notion that the leading coefficient times the degree factorial is equal to the finite difference, right? So the leading coefficient is the finite difference over n factorial. In this case, the first finite differences are constant, so it's going to be a degree of 1, right? N is 1. The finite differences here are 0.05. So this a value here is 0.05, and that leading coefficient is associated. So because we said that this is our leading term, right? This whole thing is our leading term. This is your degree. This is your independent variable. We're using s instead of x. Well, specifically, m here is your leading coefficient. So now we have the value of our leading coefficient, which is basically 0.05. Or what you could do is you could use the slope formula, and you can see that gives you the same answer because we found out what our slope is, and this is basically our slope, right? Our slope is 0.05 because we know that this is basically delta y over delta x, right? Right, this is delta y, this is delta x. Right, so technically the equation here is going to be, I'm just going to change colors here so we can kind of distinguish which steps we followed. Y is equal to 0.05x plus b, and b here is your y-intercept or your initial point, right? And in this case, E of s is equal to 0.05s plus b. We know that E of 0 is equal to 200, and E of 0 here is equal to, because we're using this point basically, right? E of 0 here is equal to 0.05 times 0 plus b is equal to 200, so therefore b is equal to 200, right? So the equation here to represent Michelle's earnings, therefore E of s is equal to 0.05s plus 200 is an equation to represent Michelle's weekly earnings. Okay, so this is a good way to kind of represent Michelle's weekly earnings, right? So you wanted to kind of identify that this was weekly earnings initially, right? So just try to be as specific as possible, right? So that's the idea behind how we can actually use this notion to create a polynomial function to model different scenarios, like real-world examples.